the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this lecture, I continue talking about polynomials, polynomial functions and their graphs, specifically the zeros of polynomials and the effect of the powers of those zeros on the graph of the polynomial itself. So prior to this, you should have already watched a lecture on, the end behavior of a polynomial. So again, this is meant for a student in a pre-calculus course or possibly a college algebra course. This can be used in college algebra as well. Some college algebra courses actually contain this material. So now that we've kind of gone through end behavior, and remember, end behavior is just kind of what happens at the edge of a graph. So it kind of gives you the idea that maybe your graph is falling forever as x goes to positive infinity and rising forever as x goes to negative infinity. We need to know, what does this middle ground look like? What's all this stuff in there? That will give us the most accurate view, almost the most accurate view of the polynomial function, its graph. So let's go ahead and define something here. And this is where, again, zeros come into play. I'm going to go ahead and erase this guy right here. Definition, the zeros of a function. Suppose we're given a function. Then c is called a zero of that function if, when plugged into the function itself turns into zero. For example, just as an aside here, maybe I'll just write it off to the right hand side. So as an aside example, if you had, for example, a function that looked like, I don't know, let's do the sine of x minus pi over 6, something like that. You know there are certain values of x that you could plug in to force that to become 0. Your knowledge of sine is assumed in this course, and you know that the sine itself normally crosses the x-axis, or in other words, its y values become 0 at integer multiples of pi. So 0 pi, 1 pi, 2 pi, and so on and so forth. Of course, that's if it was sine of x. But this is not sine of x here. This is sine of x minus pi over 6. So really, what we're concerned with is, when is x minus pi over 6, when is that equal to an integer multiple of pi? Again, where k is an element of the set of integers. And solving that, you would get that x has to be pi over 6 plus k pi. Yay. And so those are all the values of x that you could plug into the sine function, sine of x minus pi over 6, that is. That would force the sine of x minus pi over 6 to become 0. So that's the whole idea of what a 0 is. It's what you would plug in to force the function to become 0 as an output. That being said, where do the zeros of a function occur graphically? And I've just said it, actually, but it's still important to write this down. Where do the zeros of the function occur graphically? So imagine you have some random function this time. It doesn't have to be the sine. It could be any function you want. That's kind of the standard function I draw in all cases for some weird reason. And we're wondering, graphically, what's the implication of a 0? Well, by definition, a 0 is a number that you would plug in to your function to give the y value of 0. So for example, this point right here, let's just call that x sub 1, the x value. Let's call this x value x sub 2, and this x value x sub 3. If you look at that function, it should make sense to you that when you plug in x sub 1, that will be 0. And when you plug in x sub 2, again, the y value will be 0. And finally, when you plug in x sub 3, again, the y value will be 0. So that should make sense to you. And so therefore, graphically, the zeros of a function occur when the function itself crosses the horizontal axis. Most people would call that the x-axis, but it just depends on what the variable is for your axis. But I'm going to answer it that way. And I should mention that I have a habit of saying the zeros of a function occur when your function crosses the x-axis, but that's not true. It's just when the function intersects or runs into the horizontal axis. So it can bounce right off of it, but as long as it touches the horizontal axis, you have a 0 right there. And this leads us directly into this next theorem. And this theorem is critically important to understand. So suppose we're given a polynomial and c is just some real number, then all of the following statements are equivalent statements. If somebody tells you that c is a 0 of your polynomial, well, okay, before we continue this theorem, let's just kind of generate what that means. If somebody said that c is a 0 of our polynomial, then by definition, p of c must be 0. That's just by definition. Also, we've just shown that that will imply that c, or I should say x equals c, is an intercept, specifically a horizontal intercept. So this actually is the two of the results we have here. So x equals c is a solution to p of x equals 0. In other words, p of c is equal to 0. And the fourth one, c, is a horizontal intercept of the graph of p. So those three right there are pretty obvious just from our definition. The third one, though, is not so obvious. And this is actually kind of the magical piece right here. I think that this is one of the most important pieces of this theorem because it allows you to do something you need to do with polynomials, which is factor. And the only way to really convince you of this, I could do a full proof of it, but instead I'm just going to justify it slightly. So suppose that c is a 0 of p. And you know what? I might as well just go ahead and do the proof. I was just pausing the video and kind of writing that down. I thought, you know what? I might as well just do the entire proof. So let's just do the proof right here. And this is going to be specifically for part 3. The other 3, part 1, 2, and 4, they're all kind of they all kind of fall out from the definition itself. But part 3 is kind of the weird one that seems like pardon the analogy, like the redheaded stepchild. It's like the oddball in the group that nobody really knows why it's there. They have no clue as to how that blue highlighting piece kind of was generated from the yellow highlighting pieces. And because you're in pre-calculus, you should really get used to proofs and how to visualize proofs and how to go about proofs. There's a lot of different ways to go about a proof. The most common way to prove something is called a direct proof, but that's not what I'm going to use here. I'm actually, and I haven't written down this proof prior. I'm just thinking in my head how it should probably go. And I'm thinking that a proof by contradiction would be best. A proof by contradiction basically starts with you saying, well, suppose that the result isn't true, and then arriving at a contradiction. So suppose that c is a 0. So we're going to suppose that this is true, which, by the way, just implies these. We know from the definition it kind of implies those right there. Now, also, let's go ahead and assume, I'm going to write that word assume in red because that's what I'm going to say breaks here. Assume that x minus c is not a factor of p, right? So suppose that that's just not a factor of p. Now this basically means that p of x itself is not equal to x minus c times, well, some other polynomial. We'll just call that q for now, q of x. Because we're saying x minus c cannot be factored out, so therefore p of x can't be the product of x minus c and some other function. But this is actually a direct contradiction to something that we know must be true. This implies, Or maybe I should actually use language here. So this implies that x equals c is definitely not a horizontal intercept of the function p. Why is that the case? Because if you go to graph any type of polynomial, think about any polynomial one, like f of x is equal to x minus 2 squared times x plus 1. The zeros of that polynomial, 2 and negative 1, are where your curve strikes the x-axis. We know that from this and from this. And so if you take a look here, let me use blue actually. The only way your curve's going to strike the x-axis is if you have factors x minus 2 and x plus 1. That's when you have the curve striking your x-axis at 2 and negative 1. And so if x minus c is not a factor, then c itself cannot be a horizontal intercept, and thus c cannot be a 0. But this is in direct contradiction to an earlier statement that we made. The earlier statement was assume c is a 0. And now we arrive at a conclusion that says, therefore, c is not a 0. So there's something wrong here. And the thing that's wrong is where we made our assumption. Our assumption must be wrong. So by contradiction, we have shown that our assumption must be flawed. That is, x minus c must be a factor of p. Basically, your assumption, if it's wrong, then the opposite of your assumption must be true. And I don't know what's going on with my screen over there. Sorry about that. So let's go ahead and just say thus. I'll say therefore. Since I've already said thus, this is how proofs go, right? Hence, thus, therefore, additionally, moreover. Therefore, we have contradicted our previous assumption, and so x minus c must be a factor of p. Proof is done, QED. Remember, that means quod erat demonstratum, which is Latin for so it has been shown, or so it has been demonstrated. Anyhow, so that's the proof of that. I will say that there's a better way to prove that once you have the factor theorem and the remainder theorem, which we don't have right now, but I'm just letting you know there is another way to prove that that's a little cleaner, a little more solid, if you will. But for right now, I think that's very good. So good kind of introduction to a proof style as you move forward in mathematics, especially at the college level. If you have any college course worth its weight, then the instructor should have you prove things. You should go through proofs. If you have an instructor that doesn't do that, you should call out that instructor and tell them that they need to challenge you, because you're paying for the education to learn how to think critically and learn how to do those proofs. Now, I do want to go back to the theorem itself, and just so we can see it in its glory there. So now we know these four conditions are basically all equivalent. If I tell you that I have a 0 at 5 for this polynomial, then you know x equals 5 is a solution of p of x equals 0. In other words, p of 5 is 0. You also know that x minus 5 is a factor. That's the most important, I think, of these qualities. And finally, you also know that x equals 5 is a horizontal intercept of the graph of the function. So all four of those critically important, but that third one super powerful. So here's an example. Find the zeros of the polynomial. So we have this polynomial here, and it looks like an absolute mess, but we have our background of algebra, we have our background of college algebra, we have our background of trig and arithmetic, all that stuff. So we should know what to do with this. We look for common factors, or basically patterns. So I'm looking for patterns, and I see that both terms have this in common. So I'll at least factor that out. And you arrive at this guy right here. And you should note, if you haven't watched my video on advanced factoring techniques for calculus, this is a really powerful technique here where you should notice, again, patterns. This is an object, doesn't matter what it looks like, it's an object squared minus a different object squared. And we happen to know that's a difference of squares, right? First squared minus last squared is just first minus last times first plus last. I don't need to remind you of the formula, but since I've already started writing it, I just go ahead and finish it. So factoring that really quickly, I'll go ahead and do that. We get down to this guy right here. And you might be wondering, by the way, I never bothered to say why I'm factoring it, but it's because we're being asked to find the zeros. And remember in that previous theorem, the zeros occur if x minus c is a factor. And rather than trying to figure out what I could plug into that polynomial to turn it into 0, I'd rather factor the polynomial. Because if I can factor it, then all those factors, if I get x minus 5s and x minus 4s and x plus 3s, I know those numbers, 5, 4, and negative 3, are the zeros of the function. So going back to this problem here, all I need to do is a little bit of cleanup. So I'm just going to pause the video while I do a little algebra, old school algebra 1. And we get down to this guy right here. And this is actually pretty nice. It's one of my favorite trinomials to factor because it's super easy, right? That's an x plus, 2 and 3? So x plus 2, x plus 3. And remember, a sum of squares does not factor, so that's kind of locked out. So we just get down to this. And then I'm going to spend a brief few moments seeing if 3x squared plus 25x plus 8 will factor. I will use the guess and check method. In other words, I will just write out 3x and an x and then take a wild guess as to what the combination might be for the back end, right? So let's see, outers and inners. So outers being 12, inners being 2. There's no way to combine 12 and 2 to become 25, so that's out of play. But now I go ahead and try, let's see, 6 and 4. Again, there's no way for 6 and 4 to combine to become that 25, so that's out of play as well. And then I look at 24 and 1. Yep, you better believe it. 24x and 1x can totally be combined to become that 25x. So I know this is going to factor to become, and let me erase all this here so that I can make it kind of clean. It'll factor to become 3x plus 1 and x plus 8. And I'll go ahead and also erase all this silliness right here so that's out of my way. And then in black, I will finish this out. 3x plus 1 and x plus 8. I do have a video on using the guess and check method if you're interested. Otherwise, you could use whatever method you've learned from your previous course to factor. That doesn't matter. That's an Algebra 1 prereq, but if you're interested in learning that specific method, it's super fast. It can be very powerful. It also can be very tough to use if your coefficients, the lead coefficient and the constant, are highly factorable. It tends to be kind of difficult in those situations, but I think most factoring methods are at that point. Well, we now have this completely factored down, but what does that mean? Well, remember, that last theorem told us the zeros of a polynomial are actually part of the factors of the polynomial. If c is a 0, then x minus c must be a factor. And so I have all these factors, so I have a bunch of zeros here. So let's go ahead and find out. Let's see, this is actually can be written as, let's see, in blue, I'll write it down below. This can be written as x minus a negative 2. So now I know negative 2 is 0. This can be written as x minus a negative 3. So that must, a negative 3 must be a 0. Now the next one is actually the oddball. So the next one looks weird, but let me give you the trick to this. So instead of writing it as x minus a negative 2 and x minus a negative 3, it might be easier just to say what would turn each of these factors into 0. Because that's really what a 0 does, is when you plug it in, it turns your polynomial into 0. So if I had plugged in, let's say, x equals negative 3 right there, you'd have negative 3 plus 3, which is 0, and 0 times the rest of that junk is 0. So you just want to know, when are these factors 0? That's another way to do this. So x plus 2 is 0 at x equals negative 2. X plus 3 is 0 at x equals a negative 3. 3x plus 1 is 0. See, notice why I do it this way, because of that 3x plus 1. That is 0 when x is equal to a negative 1/3. And finally, x plus 8 is 0 when x is equal to a negative 8. Now, if you don't know why I'm not bothering with this very first one, let me see if I can close that out. It's in my way. If you're wondering why I'm not bothering with the x squared plus 1 is because, and if you're wondering why the x squared plus 1, I don't worry about that one right there, it's mainly because x squared plus 1 is not going to become 0. The only way x squared plus 1 becomes 0 is if x squared is equal to a negative 1, which would be the imaginary number I. So I'm not really worried about imaginary numbers. I don't think anybody's ever told you this, because they never told me this when I was a student. But when you're graphing on the XY coordinate system, the Cartesian coordinate system, the x values are real numbers and the y values are actually real numbers as well. So when you're graphing on the Cartesian coordinate plane, not the complex plane, but the Cartesian coordinate plane, you're only graphing real numbers. So you don't care about imaginary solutions or complex numbered solutions with imaginary components. So I just really don't care about this guy right here. I know there's not going to be a solution from that. So you're only worried about the real solutions. That's a short and sweet of it, right? So that being said, we have now factored, and we've used the theorem to say, well, okay, each one of those factors gives us a 0. Whenever one of these factors turns into 0, I'll have a 0 at that number. So I just set each factor to 0, solve, and now I know my zeros of my polynomial are going to be those numbers in blue. There we go. Let's see if they asked us for anything else. Nope, just find the zeros of the polynomial. That's it. Like, if you know how to factor, you know how to find the zeros of a polynomial. It's really nice. Now we step into something a little more precise for us, because when you go to graph, you need a little more precision, especially at this level. Once you're in pre-calculus and you go to graph something, you want to be as precise as possible. And this is where the conversation of multiplicity comes into play. The multiplicity of a 0, we already know what a 0 is, right? If c is a 0, then x minus c is a factor. So the multiplicity of a 0 for a polynomial function is defined to be, well, this, right? C is called the 0 of multiplicity k for some polynomial function if x minus c to the k is a factor. By the way, it's the highest degreed factor of x minus c. So in other words, x minus c to the k plus first is not a factor. So the maximal factor of x minus c is the kth power. So if you can factor out x minus 2 to the 4th power, you can. That's what you do. But if you can't factor out any more powers, then you've found the multiplicity. The multiplicity of that would be 4. So if I go back to my previous example, because this one is saying state the multiplicities of the zeros on the polynomial from example 3.2, number 6. Oh, and if you're ever wondering where I get these why I labeled them my examples like 3.2.1, 3.2.2, and 3.2.6 and stuff like that, it's because I use a Stewart, Redlin, and Watson pre-calculus textbook, I think it's the 6th or 7th or 8th edition, I forget which one it is, but it is this is from section 3.2, and this is just my 6th example, or in this case 7th example. So let's go back to the 6th example. And I just want to state the multiplicities of the zeros. Now notice when I factored here, each of these zeros had power 1. Therefore, all of their multiplicities are 1. Each of the multiplicities, so I'm going to go ahead and write these down here. I'll point arrows here. I'll say multiplicity 1. And actually, it's true for all of them. Mainly because the powers on those factors are all 1. Now, right now, if you're playing along and you've never seen this, then that's as good as you No, like, okay, well, I'm just labeling the powers on those factors. And that's literally all we're doing. But in a few moments, we'll see the ramifications of the multiplicities of a zero. But actually, maybe I'm not sure if it's in this lecture or the next. I think it's in the next lecture, but that's okay. So I'm not going to write it here because we just wrote it on the other page, but the multiplicities of those zeros are all 1. It's really kind of nice. Now let's cement this topic. Here's a polynomial. Find the zeros, state the degree of the polynomial, find the zeros, state the end behavior, state the multiplicities of the zeros. All right, so let's actually go through in order. State the degree of the polynomial. Let's start there. Degree of the polynomial. Now, if I multiply this out, which I'm totally not going to do, but if I multiply this out, I would have an x cubed from this beast right here. I would have an x squared from this business in here. Of course, I would also have an x from that, but I'm not concerned about that. I'm really concerned about the highest degreed term in each of these products. And finally, if you multiply all that stuff out, you will eventually get an x to the 7th. Yes, it will have a coefficient. I'm not really worried about that yet. I just worry about what's the highest degree term had I multiplied that piece out. And using the laws of exponents, if you have a base to a power times same base to a different power, you get to add those powers. So I'll have x to the 3rd, eventually times x to the 2nd, eventually times x to the 7th. So the overall order or degree of this polynomial will be x to the 12th. So degree, and this is the notation that we use, the degree of p is 12, because that is the overall power if you add those exponents. Notice I didn't bother multiplying that out. That'd be terrible if I did. Somebody did all the beautiful work of pre-factoring this for me. I don't want to ruin that by multiplying it out. So we have stated the degree of the polynomial. Our next job is to state the end behavior of the polynomial. Now remember, from early on in last lecture, the two characteristics you're really looking for at the beginning are going to be the degree of the polynomial and the end behavior of the polynomial. In this case, in all cases actually, the end behavior is determined not only by the degree, but by the lead coefficient, the sign of the lead coefficient. I'm going to write that down. And I can see that this might be intimidating to some people because they might look at this and say, oh, that means we do have to multiply it out. No, you really don't. Your lead coefficient, you already know, is going to be basically an x to the 12th power. But it is going to have a number in front of it. That number is going to be a combination, or I should say a product of, and I'm going to use a different highlighter for this, of this -2, any coefficient here, and any coefficient there, along with their powers. So in this case, it'll be like a -2 to the first power, because that -2 only has the first power on it, and a 1 to the second power. No reason to write that, but I'm just writing that so you can see it. And finally, a 3 to the 7th power. Now, you don't want to multiply that out. All you want to know is that positive or negative? And you better believe that is some negative number times x to the 12th. That's all I care about. Is it positive or is it negative? So the sign of the lead coefficient is going to be negative, because again, you have a -2 times 1 squared times 3 to the 7th. And so that will tell me the end behavior is just like, I'm going to grab my highlighter again. Because that's even exponent, it's going to look like a parabola. But because this is negative, it's going to be upside down. So I will chicken scratch out really quickly what the view of it should be. It should be falling here and falling there. If it were a true parabola, it would look something like this, but it's not a true parabola. so I'm going to erase that. But the end behavior acts quite a bit like an upside down parabola. If you're asked to write this using what's considered to be like limiting notation or arrow notation, you could say as x rushes off to negative infinity, in other words, as you go in this direction here, the y values drop to negative infinity. In other words, the y values just keep falling and falling and falling and falling. And on the other side, you could say, well, as x goes to positive infinity, this direction, again, the y values keep falling and falling and falling. They just fall forever and ever. So if you're asked to answer using that arrow notation, which is a tendency notation, that's how you would do it. Otherwise, honestly, when I'm quickly doing this, I just write down, down, just like that. Because it's upside down parabola, it's just down, down. Now we scroll up just to see what the next question is. We need to find the zeros. So I'm going to go ahead and erase this highlighting here and highlight that we need to find the zeros. And remember, the zeros come from the factors of this. So I'm taking a look at this. Somebody was kind enough, like I said earlier, somebody was kind enough to pre-factor all of this. So all we're asking is, when is this polynomial going to be zero? Well, I'll tell you right now, and I think I'll erase these two, just to get them out of my field of vision. We have this piece could be 0, or this piece could be 0, or this piece could be 0. It's just like you're solving an equation. You're asking yourself, if I set that equal to 0, when will it be 0? Well, when that first factor is 0, or the second factor is 0, or the third factor is 0. So let's write that down. I have to be kind of slow with my screen here because it just kind of wavers like that. So let's see, the zeros. So we have a 0 at x equals 0, again, because, if I scroll up slowly, because that first factor right here becomes 0 when x is 0. The second factor becomes 0 when x is 1/2. And the third factor becomes 0 when x is 1/3. So I'm going to go ahead and write those values down in the zeros language down below, 1/2 and 1/3. So zeros at x equals 0, x equals 1/2, and x equals 1/3. And that seems like it's not too terrible, right? Most people look at that and they're like, yeah, okay, fine. You've just basically set it equal to 0 and solved. In a way, I have. Now let's take a look at the last question. Slowly going up, there we go. The last question is asking us, what is the multiplicity of those zeros? In other words, what's the power on those factors? And so for the 0 at, well, x equals 0, the multiplicity is 3. For the 0 at x equals 1/2, the multiplicity is 2. And for the 0 at 1/3, the multiplicity is 7. So 3, 2, and 7, I'll write those down below here. So zeros, and then maybe you know what, I'm gonna write it this way. I'll make a little table here. I'll say zeros, and then there are multiplicities. All right, good enough. And x equals 0 was a multiplicity, had multiplicity 3. 1/2 was a 0 of multiplicity 2, and 1/3 was a 0 of multiplicity 7, again, because those were the powers on the factors. So this totally does not look like a terribly, terribly challenging style of problem. Right now it doesn't. And actually in the long run, I hope it's not. But we're going to use all of this information to help us graph in the long run. Now, before we do that, I just want to cement in all of these concepts. I want to give one last example here, and then we'll call it quits on this video. And next one, we'll actually go through graphing, but I just want to get this language down. So let's go ahead and go the opposite direction. Let's suppose that we know what the zeros are, and let's build a polynomial that has certain characteristics based upon that information. So they tell us we have a polynomial of degree 4. Well, what does that mean? It means that our polynomial is something, I'm not going to say equal to, actually I did say that, but I'm going to erase that. I'm going to say it's something almost like some number, who cares, times x to the fourth. But it's likely to be more complex than that. But it is a degree 4 polynomial. So check, we did that. I'm going to put a little check mark there. But they tell us we have a root of multiplicity 2 at x equals 1. Now, I do want to tell you, the word root and the word 0 tend to be used interchangeably in mathematics. So if you read the word root, you can imply the word 0. 0 of multiplicity 2 at x equals 1. Technically, there's a subtle difference between those two words, but I'm not really into telling you what those differences are. So, somebody tells you that I have a 0 at x equals 1. Well, a 0 at x equals 1 implies x minus 1 is a factor. But not only that, they tell you a little bit more. They say it's of multiplicity 2. So with multiplicity, and I use M-U-L-T just because I get tired of writing multiplicity, that implies that x minus 1 squared actually is a factor. And we have another root, or 2, that means 0, remember. We have another 0 of multiplicity 1 at both x equals 0 and x equals negative 3. So 0, again, multiplicity 1 in this case, at x equals 0 implies x minus 0, again, to the first, is a factor. But remember, x minus 0 is just x, is a factor. That tends to throw people off, by the way. If I tell you that 0 is a 0, people don't know what to do sometimes. It means x minus that number is a 0. X minus 0, which is x, is a factor. And we also were given that we have a 0 at x equals negative 3, which implies that x plus 3 is a factor. If you haven't noticed it, if I tell you that 1 is a 0, you could subtract 1 from both sides and you'll get the factor. So if you haven't noticed that, you should probably notice that now, right? 0 is not the best example, but x equals negative 3, you would add 3 to both sides, you get the factor. That's a little kind of trick to it. So I have this polynomial that was supposed to be 4th degree, and now we find out that it's actually approximately some number times x minus 1 squared times x to the first times x plus 3 to the first. Like, that's pretty solid information. That's almost completely done as a polynomial. But notice I said it's just some number times that stuff. We don't know what this number is. They have to give us one other piece of information to find that number. And they do, luckily. They tell us that that the graph goes through the point 3, comma, negative 216. Not my favorite, number to plug in here, but we're just going to do it. So if they tell us that the y value, or the output, is negative 216 when the input, or x, is 3, I can go to my polynomial and I can say, well, the output is negative 216 when my input is 3. And then you would go ahead and solve that out. And I'll slide this down a little bit. Maybe I'll even zoom in. And this implies that negative 216 over, what is that? Let's see, 24 times 3, or 72. And that's equal to k. And 72 goes in 216 3 times, so that's going to be a negative 3. Everybody knows that division. Just kidding. But at least you know what k is. Once you find out what k is, you have your entire polynomial that satisfies all of the stated conditions. So our polynomial in the end, I'll write it kind of large over here, is that k value, which is a negative 3. I have a habit of writing the x values first, so I'm going to commute that x forward. And so I have x times x minus 1 quantity squared times x plus 3. You would not be wrong writing the x in the middle, sandwiched in between those two, but I personally just like writing the smaller power of x by itself first. Anyway, that's just a personal preference. So this is kind of everything behind the scenes with zeros of polynomials and zeros of functions in general, but zeros of polynomials specifically, and how to even build a polynomial given that stuff.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.